Hello, science enthusiasts. This is Osama Al-Amrani. I am a grade 11 student at Al-Nada School in Sana'a, Yemen. Whether you're a curious student, a lifelong learner, or just someone who loves the wonders of the universe, you're in the right place. Today, we're diving into the periodic table, the ultimate cheat sheet for the universe. It's the master key that unlocks the secrets of everything around us, from the tiniest atom to the vastness of space. It's not just a classroom chart, it's a map to everything you can touch, see, and even things you can't. Every object, every breath, every star in the night sky is connected to this table. Every bit of matter, from the air we breathe to distant stars, is made of elements, and this table organizes them all. It's the foundation of chemistry, physics, and so much more. The periodic table arranges 118 elements by atomic number and groups them by similar properties. This clever design helps us make sense of the building blocks of the universe. This organization reveals deep patterns in nature and lets us predict how elements behave and interact. It's like having a scientific crystal ball. On the left, reactive metals, ready to spark and react. On the right, stable gases, calm and unreactive, perfect for lighting up neon signs or filling balloons. In the middle, versatile transition metals, the workhorses of industry and technology. The bottom rows, special elements with unique properties, often used in cutting-edge science and technology. The table's genius, first envisioned by Dmitri Mendeleev, is that it didn't just organize known elements, it predicted new ones, changing science forever. Mendeleev left gaps, forecasting elements yet to be discovered, and even predicted their properties with remarkable accuracy. So, let's explore this map, one element at a time. Consider the science and get ready to unlock the mysteries of the universe together. Let's decode the table's structure, rows and columns. The horizontal rows are periods, 7 in total. Each period adds a new electron shell. As you move left to right, elements gain 1 proton and 1 electron, shifting from reactive metals to stable gases. This repeating pattern is why it's called the periodic table. The vertical columns are groups or families, 18 in all. Elements in the same group share similar chemical properties because they have the same number of valence electrons. For example, Group 1 alkali metals are soft, shiny, and react explosively with water, all thanks to a single valence electron. Group 17 halogens have 7 valence electrons, making them highly reactive and eager to gain one more. Periods show energy levels. Groups reveal family traits. This structure lets us predict how elements will behave. That's the power of the table. Let's zoom in on a single square of the periodic table. The atomic number at the top tells you how many protons are in the nucleus. This defines the element. In a neutral atom, protons equal electrons, balancing positive and negative charges. The atomic mass, usually a decimal, is the average mass of all naturally occurring isotopes. Isotopes are atoms of the same element with different numbers of neutrons. To find the most common number of neutrons, round the atomic mass, subtract the atomic number, and you've got it. For carbon, atomic number 6, mass about 12, so 6 neutrons. These two numbers, atomic number and mass, unlock the identity and structure of every element. With just a glance, you can figure out protons, electrons, and neutrons. That's the magic of the periodic table's design. Every box is a mini biography. Let's keep exploring. Electrons don't just float around randomly, they're organized into shells, like planets orbiting a star. These shells are specific energy levels, and each one can only hold a certain number of electrons before the next shell begins to fill. The first shell holds just 2 electrons, the second can fit up to 8, and the third can hold as many as 18, though it's most stable with 8. This pattern continues for larger atoms, with each new shell able to accommodate more electrons. The arrangement of electrons, called electron configuration, determines an element's chemical properties and how it interacts with other atoms. Let's look at sodium, which has 11 electrons. 2 electrons fill the first shell, 8 fill the second, and 1 lonely electron sits in the third shell. This single outer electron makes sodium highly reactive, eager to lose it and achieve a stable configuration. Valence electrons, those in the outermost shell, are the key players in chemical bonding. They determine how atoms connect, share, or transfer electrons with others. Elements in the same group of the periodic table have the same number of valence electrons, which explains why they behave so similarly in chemical reactions. For example, Group 1 elements all have one valence electron, making them highly reactive metals. Group 17 elements have 7, making them eager to gain one more electron. As you move down a group, each element adds a new electron shell, making the atoms larger and changing their reactivity. Across a period, from left to right, electrons fill up the outer shell, gradually changing the element's properties. Noble gases in Group 18 have full outer shells, making them extremely stable and almost completely unreactive. The shape of the periodic table itself reflects these repeating electron patterns, with rows and columns organized by shell and valence electron count. Understanding shells and configurations unlocks the periodic table's predictive power, letting us anticipate how elements will behave. Now let's dive even deeper into the architecture of atoms and see what other secrets the periodic table holds. The Bohr model is a start, but real electron configurations are more complex. Each shell contains subshells, S, P, D, and F, with different shapes and capacities. The S subshell holds 2 electrons, P holds 6, D holds 10, and F holds 14. The periodic table's blocks reflect which subshell is being filled: S block, groups 1, 2, P block, groups 13, 18, D block, transition metals, and F block, lanthanides and actinides. The S block is 2 columns wide, P block is 6, D block is 10, and F block is 14. This structure isn't arbitrary, it's quantum physics in action. The table's shape is a direct map of how electrons fill up subshells. Chemistry's patterns are written in the table's architecture. Let's look at how these patterns affect atomic size and energy. The periodic table reveals trends, like atomic size and ionization energy. Atomic radius increases as you move down a group, more shells, but decreases across a period, stronger nuclear pull. As you go down, atoms get bigger, across they get smaller. Ionization energy, the energy needed to remove an electron, decreases down a group, outer electrons are farther away, and increases across a period, nucleus pulls electrons tighter. Metals on the left lose electrons easily, non-metals on the right hold them tightly. These trends explain why elements behave as they do, why sodium reacts explosively, and neon doesn't react at all. The table's layout is a map of atomic behavior. Understanding these trends lets us predict reactivity and bonding. The periodic table is more than a list, it's a pattern book. Let's explore the push and pull for electrons. Electronegativity measures how strongly an atom attracts electrons in a bond. Think of it as electron greed. It increases across a period, atoms get hungrier for electrons, and decreases down a group. Outer electrons are farther from the nucleus. Fluorine is the most electronegative, francium the least. Electron affinity is the energy change when an atom gains an electron. Halogens have the highest affinities. Electropositivity, or metallic character, is the opposite. It increases down a group and decreases across a period. Metals lose electrons easily, non-metals gain them. These trends shape the types of bonds elements form. The table's trends are the key to understanding chemical reactions. Let's visit the table's most interesting neighborhoods. The periodic table is a city of neighborhoods, each with unique traits. Transition metals, D block like iron, copper, and gold, are versatile, form colorful compounds, and act as catalysts. Their D electrons allow for multiple oxidation states and vibrant chemistry. Halogens, group 17, like fluorine and chlorine, are highly reactive nonmetals, always seeking one more electron. They form salts and are powerful oxidizers, never found alone in nature. Noble gases, group 18, like helium and neon, are the table's aristocrats, stable, unreactive, with full outer shells. Their stability makes them perfect for inert environments and lighting. These groups highlight the table's diversity, from reactive metals to stable gases. Each neighborhood has a story, shaped by electron configuration. The periodic table is a living map of chemical behavior. Let's see how ions and bonding fit into this grand design. The journey continues. Atoms are not always neutral. They can gain or lose electrons, transforming into ions. These charged particles are the true drivers behind countless chemical reactions, shaping the world around us in ways both visible and invisible. Metals, found on the left side of the periodic table, tend to lose electrons easily. This loss turns them into positive ions called cations, which are essential in forming many everyday materials. Meanwhile, nonmetals on the right side have a strong pull for electrons. When they gain electrons, they become negative ions or anions, which play a crucial role in countless chemical processes. The group numbers on the table help us predict the charges of these ions. Group 1 elements form +1 ions, Group 2 forms +2, and Group 17 forms 1. This pattern continues across the table, making it a powerful predictive tool. When oppositely charged ions meet, they attract and bond together. This ionic bonding creates stable compounds, like the table salt we use every day, and is fundamental to chemistry. The periodic table is more than a list. It lets us predict which ions will form and how different elements can combine to create new substances. It's not just a chart, it's a powerful predictive tool, helping scientists imagine and create millions of compounds that make up our world, from medicines to materials. The table organizes the building blocks of matter, revealing hidden patterns in atomic size, energy levels, and how reactive each element is. It explains why some elements, like sodium, are highly reactive, while others, like noble gases, remain stable and unreactive under most conditions. By mastering the table's structure and understanding its trends, like electronegativity and ionization energy, we unlock the secrets of chemistry and the behavior of matter itself. The periodic table is a scientific masterpiece, a map that guides our quest to understand the universe, from the tiniest atoms to the most complex molecules. So keep exploring, stay curious, and let the periodic table be your guide as you unlock the mysteries of chemistry.